thought I would make a video about what you need to know at this point. I began to think about the different topics that we've covered. I went back and I was just making out the benchmark. I was going through different things, and I looked at the different concepts, and we talk about a lot of different things all the time. But I kept coming back to one specific question each time, and it really kind of plays into the part of what do I really know, or what should I really know at this point. And a lot of you probably don't know all of the different aspects, and that's okay. I don't expect you to be professionals at this in 6 weeks. Okay. In fact, I don't expect you to be really good at much of it. But what I do expect is that you're growing, that you're getting better every day. That every day you take a little bit, you take another step to getting closer to knowing exactly what to do. And in statistics, knowing exactly what to do isn't necessarily always one answer, and that is frustrating. So what I'm going to do is I'm going to take the chapters 18, 19, 20, 21, 22, and I'm going to detail them out. I'm not going to hit every topic. You're going to see in a minute that I have 3 pages I want to go through, and there is a ridiculous amount of information on each page. And so without overwhelming you, I'm going to take each one, kind of run through that a little bit at a time, and I don't know that I'll be able to go into as much detail on each page, but I'm going to make this available in print so you can print it off, or maybe just keep it on your computer or your mobile device, and you can take it yourself and you can look at it and examine all the different parts on it. And so we're going to start off just by kind of looking at the first page, which is that. And that's a lot of information, but that is some really good information. I want to kind of just zoom in and talk a little bit about this piece. Chapter 18 was sampling distribution. Chapter 18 really brought in this central limit theorem. Okay, the central limit theorem right here says that I need to know this because this is the central, not just because it's called the central limit because it talks about things happening at the center of the distribution, but this is the statistical foundation. This is what a lot of statistics is based on. So it's really important that we know that. And I've got a little bit, you can see that here. This is a clip off of a website that I thought had a pretty good summarization of the central limit theorem. And I'm not going to read that to you. You can read that on your paper yourself. And you should know this. The central limit theorem was illustrated when we did that through the Penny Lab, right? We talked about as you increase the sample size, right? It says how large is large enough. It says large is a sample size of 30. That would be the quantitative version. If you take a sample from any distribution, it doesn't matter if it's skewed or bimodal or anything, if the sample size is large enough, then that distribution is going to be a normal distribution. And we see that, and we've seen that over and over again. Some other things. I'm just going to kind of run through this fairly quickly. You've got these pieces here. We had to decide between categorical and quantitative. You have the standard deviation for p hat, standard deviation for this. Eventually that became standard error. In chapter 19, it became standard error for p hat and standard error for x bar. And these were the 2 formulas we had to deal with. Remember that if you have a sample size that's larger than 1, I have to recalculate standard deviation. If you remember, the variability always decreases as sample size increases. You can read that over in this section here. As the sample size increases, that's what standard deviation is going to reduce by changing that value for n, and it's going to make it smaller. Parameters, okay, those are mu or p. Those describe the population. Statistics come from x bar and p hat. Those describe my samples. Calculator functions that we've talked about, all right? And so you see here normal CDF and inverse norm. I don't think I need to really go into a whole lot about this. This is something that you've seen quite a bit. Normal CDF, upper lower values, your mean and standard deviation. This gives us percentages. It gives us area under the curve, probability. Inverse norm is just the inverse of that. We have to use the percentile to put into that. And if you remember, the percentile, it's the total area to the left of the boundary. Whatever that boundary happens to be, if that's if it's 5%, if it's 95%, it doesn't matter. You need to make sure that you understand what percentile is. All right, if we go back, I wanted to remind you that, remember that you can get a z-score, in chapter 23 and beyond, t-scores by using the inverse norm or inverse t for quantitative if we keep the mean and standard deviation equal to 0 for the mean and standard deviation of 1. So if we plug those in there, that result would give me a z-score, right? But it can also give me numbers in context of my problem. So if I have this here in for the number, if I type in the mean and standard deviation given to me in the problem, then that inverse norm function is going to give me back whatever the number is in context of the problem. If it's miles per hour, or if it is grades on a test, or public opinion on a certain percentage of people that voted for a candidate, it's always going to be in that context. Okay, and just to kind of redefine some of these things, P, anytime you see P, and not in context of a significance test, this is just like a parameter. P, usually we write out the word p-value. So if you got in the habit of writing P equals at the end of a significance test, it might be a little safer to write the phrase p-value instead. I know that I go back and forth between the two. Usually it's not a big issue, but here, P is the population proportion. It is a percentage of the population. It's fact. It's truth. Okay, P hat comes from a sample, and they represent the same kind of idea, but this is from a sample. It's from a smaller portion of the population. Population mean for quantitative data. Remember, if we use the word means, that's quantitative. We use the word proportion, that's categorical. X bar would be the same as P hat, but in the quantitative sense. It's a sample's average, right? And N, in either case, represents sample size. Sigma, which is my population standard deviation, and S, which represents my sample's standard deviation. Now, not to be confused with my formulas from here. Yes, this does represent the standard deviation from the samples, but remember, the S they give you would be the standard deviation for a sample of just a selection of 1. If you choose a selection of 5 or 10 or 100, then I have to go ahead and continue to change my standard deviation, because standard deviation changes based on these two formulas you see here and here, because they have, obviously, a formula that requires the use of n, and it shrinks every time that you increase that value for n. If we go on down, well, one more thing, kind of bold there. A statistic is an unbiased estimator of our parameter. That's a phrase that you should know, and you have to understand what the word statistic means. You have to understand what the word unbiased means, and the word parameter. If you don't know what a statistic is in relation to a parameter, if you don't know what it means to be biased or unbiased, then you can say that, but you don't know what it means, not really what it means. So take that to heart and think about what those words mean. Do you really grasp what that says? Because this is essentially what we're doing in a confidence interval or a significance test. We're trying to estimate some value, and we want that to be unbiased. That's part of our assumptions and conditions. Okay, so let's go on and talk about confidence intervals. A lot of stuff right here. Let me kind of go a little further. A confidence interval, in general, you can see right here, in general, it says it's an estimate plus or minus my margin of error. That's all a confidence interval is. I have an estimate. I get a sample. I got a p hat. I got an x bar. It says, oh, the average is supposed to be this. But I'm not totally sure that that's exactly what it is, because it's just a sample. It's not from the population. I don't know that that number is exactly what it's supposed to be. And so when you have here a confidence interval, you have the formula for the interval down at the bottom here, and I can plug in all the values that I have. P hat plus or minus z star times p hat times q hat over n. Remember, in a confidence interval, you do not know p. You simply know p hat because I'm trying to estimate that unbiased estimator, which is my p, which I'm not going to know, or I wouldn't be doing the confidence interval. And I have highlighted there, you can see at the bottom, S sub e, or SE is p hat of p hat is equal to the standard error. And the margin of error is that times z star. And so you can see that combined gives you your margin of error. If we go down to the bottom, you can see down here, you have the confidence interval is always two-sided. I just wanted to make sure that you understood that. I'm not going to read all of this to you. I think you can do that for yourself. You can see here there's two different interpretations. One, confidence level. What does the 95% mean? And confidence interval. Now I chose, I made up an interval at 95%, 0.47 to 0.56. And I think there was an example in the book that talked about global warming. So I totally made that up. That's totally not accurate. But if I were to get that result using that kind of confidence interval, then my result would be I'm 95% confident that between 47% and 56% of the U.S. adults think that global warming exists. That's what that confidence interval interpretation is. The confidence level means, well, what does 95% mean? It means 95% of the samples that you create, or we're not going to create a sample, but 95% of the samples of samples like this one, depending on whatever size it is it's going to produce an interval that also captures that unknown parameter of the number of adults that think global warming exists. So 95% of those will contain that real values as well. 5% of them will be the unfortunate ones. It'll be the ones that we just unluckily get a bad sample. A couple other details about confidence intervals I wanted to make sure that I said and put on video so people can have a chance to go back and look at it and we talked about this in class, the interval, the confidence interval itself is 2 margin of errors wide because I take the proportion or the mean, depending on quantitative, I add 1 and I subtract 1. So it's essentially making it 2 margin of errors wide from top to bottom. Okay, with greater confidence, you have wider intervals. Okay, so we have greater confidence, wider intervals, and lower precision. All three of these things happen together. So if I lower the confidence, the interval gets narrower. The precision increases. Remember, precision and confidence are always a give and take. The example I used in class was the weather forecast when he had 100% confidence. The weather forecast was, it's going to be negative 200 to positive 200. Yes, he has incredible confidence in his answer, but it's so imprecise that it's useless. And so you kind of have to play around with that. All right, and one other thing was that greater the confidence is, the larger the margin of error. That kind of goes with what I said earlier, but I wanted to specifically state that because the confidence level, when I change my confidence level, I'm changing the Z star or T star, and that's going to magnify that margin of error by whatever you change it to. And that is chapter 18 and 19. Okay, in a nutshell. That's not everything. Obviously, I couldn't put everything on here, but those are some of the most important parts of those two chapters. Let's go ahead and talk about 20. Oh, yes, 20. Oh, yeah, see this right here? Big deal. I wanted to talk about a little bit just the parts of here that you had that are the most important things that I need to know conceptually. It's nothing that's necessarily that I have to do or calculate, but it's things I have to be able to do to actually get all of this stuff done. And so the first part is we started talking about confidence intervals, right? And then we talked about significance tests, and the biggest difference is in a confidence interval there are no hypotheses, but in a significance test there are. So I had to learn how to write a hypothesis, a null and alternative hypothesis, right? My alternative is that it's one-sided? Is it two-sided? Do I use not equal to? Do I use greater than or less than? When do I use equal to in my null, which is pretty much always? I needed to be able to write those. The second thing was we had to really, really get into checking our assumptions and our conditions. And I know that can be tedious and frustrating, and it seems like it's a waste of time, but it is required. It's something that has to be done. Interpretation of p-values in context. That is such a big deal, because if you can't make that conclusion, if it doesn't make sense to you, then you don't get it. You haven't gotten to the point where you can make sense of your answer. It's not quite clicked for you yet. Okay, some of you are getting there, and I see lots of good things. Keep doing what you're doing. Just keep trying and keep answering. Keep reading the context of the problems in the book, or the things that we say in class, or the answers that we use on the significance test from maybe the old AP tests. Those are really good too. And here, you got down at the next part, which is how the test statistic, which could be a t-score or a z-score, and the p-value work together. We talked a lot about that today in class. Question number 3 on the test from chapter 20 kind of played that out. It wasn't necessarily a p-value you're working with, but you had to figure out when I'm rejecting or failing to reject the null based on a test statistic, a z-score, not a p-value. Confidence levels, confidence intervals, and how significance tests correspond or not in certain situations. Now, it's not very common that you do a significance test and a interval at the same time. It's usually not done because it's kind of redundant. I don't need to do them, so I don't go that far. But it's good to know how they connect and when they don't connect. Alpha levels, which is called my significance level, or we could also call it a level of proof. In several questions we talked about, you had that down at the bottom, the level of proof that you were working on. Okay, so these things are not, these aren't optional. These are some things that you really, really need to know how to do. All right, so let's go in and let's talk about null and alternative hypotheses just for a little bit. The null is the fact that I'm going to write out, they're going to be expecting something to happen in context of the problem. So my null is going to be the fact that, oh, this thing's not happening. It's not there. We're going to assume that there's nothing going on. So it's the no effect, or the no difference, or the absence of whatever effect is being desired at the time. Typically, we say that it's going to be equal to whatever the assumed value is before this question ever came up. The alternative is what we're going to conclude if we find that null hypothesis to not really be as possible or as likely as we started off thinking. Okay, and notice there I didn't say it was false. I didn't say I'd proven it wrong. You never will with the significance test. But it doesn't seem to be very likely, or our probability, our p-value, is suggesting that the alternative is more likely to occur than the null would be likely to occur. Okay, and I kind of wrote down a few things. When you have an alternative, right, we could use less than, we can use greater than, and these two things are what we call one-sided alternatives. Right, I drew out the curves. Less than is, of course, the area is all less than. It's always on the left. Greater than in the area is always on the right. You can see that there. Then the two-sided alternative, which you see underneath that, is the not equal to. If you can't draw these curves when you're doing a significance test, if you can't put the mean in place, and you can't put down the number you're testing against and shade that in and figure out what the probability is, and then which is your p-value, or even put the alpha level down and kind of correspond that to the p-value, you need to work on that. That's something that's really important, to be able to write these curves and show them and write down exactly how they play a part with each other. Okay, and I highlighted a statement here, and this is kind of what we're trying to do with a significance test. Right? It says, when we conduct a significance test, the assumed truth of the null is what we're trying to check. That's what's under suspicion. And the question you're trying to answer is, do you have enough evidence that would lead you to think that the null hypothesis is more likely to be true than the null? And that's the process that we take. And I want to do an example. We're going to look at the example on page 525. It's number 15. It's about twins. And the problem, the P, the proportion that we're investigating, asks, and it gives some background, which I'm not going to read. You can look that up. Does this, and as the information they gave you, does it indicate an increase in the incidence of early births of twins? You're comparing two different years, in 1990 and in the year 2000. And they have two sets of data, and you can see that set of data over on this side, over here. And the question is that enough evidence? Is that result of my sample? That's a typo right there. You're going to have to ask the question, are these two samples enough to make sense that they're different from one another, or they're exactly the same from one another? All right, let's see. That's 26 for X. Let me change that. There we go. So you have this sample, and you can see, and I'm going to go through the whole thing. I drew the curve out, and originally on the curve I had drawn the population curve. I drew the proportion P at 0, right? I'm looking right here at P equal to 0 because I want to know, is the difference equal to 0, or is there a significant difference in the two, so that suggests that one distribution is different from the other one. And so we'll just start off with our hypotheses. And so what I did was I went down here and I said, well, I'm going to say that they're equal to one another. P of 1990 is equal to P of 2000. And the alternative, remember what we said earlier, is there an increase in the incidence of twins? So is there an increase, meaning is the year 2000 greater than the year 1990? So as time progresses, do you have an increase in the proportion of those births? And notice that my alternative says less than, but yet the problem says increased. And here's where it comes into play that you as an individual have to be intelligent in your choices, and you have to think about it, and you have to look at the problem. Here, I'm looking at, I know that 2000 has to be more than 1990. So just because it says increase in the problem, I didn't choose greater than. And I could have written it such, if I had drawn 2000 on the left side, I would have chosen greater than, right? But my first, when I go into the calculator and I type all this in, when it says X1 and P and N1, my 1 data, right, that's going to be from 1990. And my 2000 data would have been in X2 and N2. If I had done this backwards and I had put 2000 first, then I would have chosen greater than. Make sure that you understand the choices for your null and alternative. Okay, and the next part would be going through my assumptions and conditions, and I'm not going to bore you with all of that. They all check out. You can check out randomness, independent groups, 10%, and of course my success or failure. So all these and things check out to be just fine. There wasn't any question about whether they work or not. The test we're going to be using is a two-sample or two-proportion z-test. We have two different samples from two entirely different years, a decade apart. And so this is clearly a two-proportion z-test. This is categorical. The question was, were the twins born early or not? And so it was a yes or no type of question. All right, so the the z-score would have been negative 0.7292. And immediately you look at that and you think, that's not very big z-score. So you probably can guess at that point you're really not going to reject your null, because typically we want to see standard deviations or z-scores, upwards of 2 or more to end up rejecting my null. Not exactly, because it depends on your alpha level. In this case, we have O, which is my p-value of 0.2329. And in this case, I could have chosen an alpha level of 0.05. It really wouldn't have mattered because my p-value was quite large in this case. And so my conclusion kind of takes that into account. It says since our p-value of 0.2329 is high, more than any traditional alpha level, we would fail to reject the null. There is no evidence of an increase in the proportion of preterm twin births from 1990 to 2000, at least not for this particular hospital. Now, why would I have added that portion to the solutions? because this sample was just from that hospital. And even though, and you can read up when I put down at the top, it's not technically random because it all was from one hospital at one particular time. It would be representative of the twin births. I don't have any reason to think it would be biased. And so I wanted to put that in there. Was that required? Probably not, but that's why I put it in. Okay, so that's, in general, that's a significance test. That's kind of where we started. That's where we went with the significance test values. Let's go ahead and go on and talk about a confidence interval. All right, so I looked at problem number 24. This is on page 526, and this is about cheating in high school students. Reuters University did a study about high school students, and they wanted to know if they cheated on at least one test. And so the result was that out of 4,500 students, they asked nationwide from a random sample of different high schools across the country. They said 74% of the students said they had cheated at least one time on an assessment of some type. And the question we're going to ask is, this was a sample, but they're investigating the true value of how many students cheated across the country in high school. And they want us to estimate that number, even though we have really no way of finding out. I mean, no one's going to go out and ask everybody. Not to mention, you probably are going to get some sampling bias. This is a kind of a sensitive topic. You know, we talked about people when you have to ask things and you have to admit to things that were wrong. People tend to lie about that because they don't want to seem like they're being looked down upon or whatever. All right, but if we do this, I'm going to kind of walk you through this confidence interval step by step by hand, and then we'll talk about the calculator portion. So the confidence interval is, of course, estimate plus or minus the margin of error. And so you got plus or minus or 0.74. That was our estimate. They told us that 74% from the sample cheated. Well, I'm trying to get the range of values that I think, well, based on the sample size I took, I think the true proportion probably falls within this range. Pretty big sample, so I think I'm going to be pretty close on what my sample says, but we'll get a little range on that later. And so I find my standard deviation, or my standard error, 0.74 times 0.26, divided by 4,500, and that gives us 0.0065 down here at the bottom. And so, scroll up a little bit. You see, I picked 90% confidence, or they picked 90% confidence, and we got our Z-star based on that confidence level. And then I just went ahead and plugged all this into the formula here. I went ahead and changed that into its decimal form. And then I went ahead and multiplied and got the margin of error just as a step to show you this is my margin of error. Remember the estimate up top says estimate plus or minus margin of error. Well, what is my margin of error? In this case, it's just over 1%. So I have 0.74 plus or minus 0.0108, and this is all done just by using the formula for confidence intervals and margin of error. Right? So I did it by hand, and that was my results. 0.7292 was the lower value, and 0.7508 was the upper value. And that was because I rounded the numbers, but then I went in my calculator and I typed in the values, and I did a 1 proportion Z interval in the calculator, and I got these values. And so you can see how exact even the formula can be, even though you're, because if I were to round those two at the bottom to four decimal places, then I would still get exactly the same as what I had by hand. And so then I kept 4 in my numbers anyway, so that would be fine. All right, if we go back, before we get too far into it, if we check, let me go down here. Check our assumptions and our conditions, right? All of them are satisfied. And so you had students are cheating. They're independent in the choice of cheating or not, and it was told to us that it was a random sample. You have 10%, which is plenty. 45,000 students. There are more than 45,000 high school students in the U.S., and the success or failures are well over 10, so that you know that the sample is large enough. If I were to write out that conclusion, you can see at the bottom of the screen there, it says I'm 90% confident that between 72.92% and 75.08% of students in high school cheated on tests, or in the U.S. cheated on tests. And this is just a simple explanation of or interpretation of that particular interval. And just to kind of go back, I want to talk about the curve for a minute. This nice pretty curve in the center. And I've kind of explored this, kind of went a little overboard, trying to show you all how it plays apart, how it's all broken up and divided up. In a confidence interval, the confidence interval is always centered on the mean or the proportion that comes from the sample. Well, they got 74%, or it was 3,300 students out of the 4,500 students that admitted to cheating. And so that was where my center comes from. The numbers on the sides, now I used inverse norm to get mine. I didn't have a table of values right next to me. And so I simply did inverse norm, and I showed you what I typed in to get those values. I know there's 5% at the bottom, so to get the bottom z-score or the top z-score, I type in the appropriate percentile using 0 and 1. That gives me my z-scores. Once I've got that, I can figure out, okay, well, there's my z-scores, and I can look at it from there. Just kind of, I don't know that you understand this, but if I were to go in and do normal CDF over here, and I use the z-scores, negative 1.645 and positive 1.645, what I have over on this side, with 0 and 1 as my mean and standard deviation, it's going to give me 0.9 because it's 90% in between the two. So that should click. That you should know that. Okay, so let's kind of finish up that question, and we'll be done. Here's an interpretation of the interval itself. 90% of the samples of sample size 4,500 would produce a confidence interval that would contain the true proportion of high school students that cheated. Self-explanatory. And then part D, it's asking, is 95% going to be a wider interval or a smaller interval? Well, 95% increases your confidence level, which means my z-star would be a larger number. In fact, it's 1.96. So when I multiply 1.96 times the original standard error, then it's going to get even larger than it would be this way. This kind of goes back to the first image we had. Higher confidence, higher margin of error, wider interval. And these are just a few of the things. Yeah, that's it. These are a few of the topics. I mean, a few is not a few. A few is a ridiculous amount of information that you're supposed to assimilate and be great at in just a short amount of time. And that's the key there. It's time. A lot of you are very busy, and I totally understand that, right? And so you've got to carve out that time somewhere because you've got to spend time. This has to soak in. It has to kind of work its way through before it really starts to make sense. So give it some time, put forth your best effort, and by all means, check out the videos, check out the class after school. If you can come after, ask questions, take time and do what you need to do. Please don't hesitate to ask me for anything that you need for help.